Jazayeri, and their topic is simple optical character recognition using machine learning.
Good afternoon, everybody. Today we're going to be talking about simple optical character recognition using machine learning. I would like to say that optical character recognition is widely used in the society of today. For example, in the educational sector, we kind of use it. For example, when objective sheets are being marked, lecturers can take the objective sheet and then pass it through an OCR machine and it marks it very accurately and fast. Also, we can also have it in, for example, document retrieval in journalism or media communication industries, where a document that is partially destroyed is also passed into an OCR machine, which is implemented by machine learning, and then it tries to predict what the lost data was, or the lost character is. OCR automates the process of converting text within images into digital text format. So how it just basically works is that it takes an image and then it tries to interpret it into digital text format, so it converts it. This project is, first of all, I would like to say that there are several algorithms that can work with this, but then we chose convolutional neural network, which is good for like prediction of data sets. This project is a convolutional neural network to create an OCR system for converting handwritten text into digital format. I think my colleague here is going to.
My name is Delight Fichukwazogo, and I'll speak on the significance of the project that we did. It is used for educational values, help students and beginners understand how OCR works without advanced infrastructures of preprocessing. So an OCR system or an OCR engine usually have the industry standard OCR system have a lot of preprocessing to get the data or the test data or the input data to where their model could process it and predict it. This does not have all of that, and it just gives you the fundamentals so you would understand the actual concept of OCR and not the pre-processing of the data. It's also resource efficient, so because of the title said, it's simple, so it can run on low resource systems like Raspberry Pi, mobile devices, although most of them have the capacity for much larger or for the slower and older devices. And also, this project is not a replacement for OCR engines because those have more better preprocessing and more better data trained, and so it performs better in much larger scale of test data and all of that.
So we're going to be talking about the implementation of how we implemented our optical character recognition system. So first of all, we have to develop the model. It's a convolutional neural network. So we have an input image, we have an image, and then we have several hidden layers. For here, we try to keep it very simple because of the nature of the data set. We make sure to have like 4 hidden layers, and then with each hidden layer having activation functions. We also make sure that those activation functions is ready because those are what perform best with CNN, and then at the output layer we use the softmax activation function. So pretty much our CNN model was designed and trained to classify the characters. The architecture optimization methods and training regimen were crafted to maximize accuracy and minimize overfitting. So with the nature of our data set, it's very prone to overfitting actually. because we are dealing with handwriting, and several people have different types of handwriting and how they are able to, depending on their posture, depending on the size of their hands, and several other aspects. But then our model was by we were able to improve our model by tuning the hyperparameters and also training it for a longer period of time to be able to get a more accurate output. Thank you.
Yes, first of all, the data processing. So this is collection of the data and removing any pretty much redundant data or data was taken from cargo. Our data set, and it consisted of 0 to 9s and A to Z in both lowercase and uppercase characters. And our data was about 52,000 characters, 52,000 pictures. So the composition, the training set included labeled grayscale images, 1 character per image. The images were collected from the combination of open source data sets and synthetically rendered using common fonts to have broad coverage of size, fonts, and styles. So the data were grayscaled by our work from the cargo, and we pretty much use those and they had different fonts and different styles, to them different sizes as well, and they were resized to a 64 by 64 pixel image for faster training and better pretty much feature extraction.
So we have the normalization and image scaling. Actually, because of the nature of our data set, we have a wide range of values of the pixels. So for example, normalization just helps to reduce it to a certain range, which is from 0 to 1. We have data cleaning, data integration, and data reduction and data transformation. Also, I would like to know that we also split our data into the train, test, and validation data sets in the ratio of 70 to 15 and 15. So this is basically the architecture of our model. We have a convolution layer, which input layer goes into it, and then we have max pooling, which basically just selects the important features and then drops the rest. We also have the second convolution layer, max pooling. We have the third convolution layer, and then we have the flattening. The flattening basically just converts the pixels into one dimension, and then we have the dense layer, which also makes sure that the data set, the pixels are fully connected, and then we have dropout layer that drops out the unnecessary data, and then we have dense layers also. For our data sets, we made sure we had a total of 7,699 parameters, 776, and then that's like basically the code implementation with the activation layers and whatever.
And we were able to get a 96.8% accuracy from our training. We had a different data set for training. This consisted of handwritten data, and we had some missed predictions as well that came from similar characters with different handwriting. Like the one above there, the data there was labeled as a 1, but it was predicted as an L because they were a 1 and an L are very similar in lower and lowercase l. And then we also had a Z there, that's the lowercase z, and as you can see, it ignored because some people write their Z's with a cross in between to differentiate it from the 2. So, and our model was also able to pick that. And the future work that can be done is more pre-processing of the data for a better accuracy across documents. So because we have a lot of different size fonts and everything, so you can have feature like ongoing of the image, better resizing of the image, better algorithm for resizing of the image, sharpening of the image as well, and then segmentation for documents, segmenting each line to be and each character in like a big document. And yeah, that's the conclusion. The system was created using a tensor-based CNN, tensor-based computation and neural networks, and obviously, as you said, we had a 96.8% accuracy. Overall, the work offers an accessible foundation for OCR in educational, experimental,